arsenic, cadmium, mercury, and lead. And this poses health risks, especially for children. These are some Okay, so we go to active remediation. Reprocessing removes the contamination source rather than containing it, recovering critical minerals while cutting acid mine drainage risks. Also, we have jobs in local economy. This sustains skilled and semi-skilled employment, extending a mining district's economic life. We also have community benefit sharing. Obuasi shows the model scholarships health programs such as skills training and also not wages alone. Now we are going to look at Ghana's feasibility case using the economic lens. We have a chart here, and then from this chart, we can see that tailings reprocessing costs $11 per ton in OPEX, compared to $120 in primary mining. And then also, WASA has an I should skip on that. Okay, WASA has a lower ore grade of 0.1 grams per ton, but yields 81.5% recovery due to the use of conventional CIL or CIP under higher grade, but Bob also yields a higher grade of 0.85, but yet yields 38.5% recovery because they need biooxidation pre-treatment. Moving on to the policy lens, global best practices versus Ghana gap. Jurisdictions such as South Africa and Australia shows us what works. 1, tailings is legally recognized as a mineral resource. 2, there is clear ownership rights over historical dams. 3, there is well-developed, predictable license. 4, there is targeted incentives and research findings. And also we have Ghana gaps. 1, no policy dedicated to legacy tailings reprocessing. 2, there is unclear ownership after mine closure or license expiry. 3, there is complex and multi-agency permitting causes delay. 4, limited financial incentives versus Australia. 5, we have incomplete data on historical tailing sites. Now we move on to the case studies. 3 countries, 1 emerging playbook. DRD Gold Ego in South Africa process over 20 million tons per year using hydraulic mining of old dams and CIL recovery. This helps to remove historical dams from urban Johannesburg, cutting dust and acid mining drain risk. 2nd, New Century in Australia, focusing on zinc, lead, and silver, uses dredging, flotation, and filtration. This is built as global tailings retreatment business model around green metals. 3rd, bringing it home to Ghana, Obuasi Mine. Obuasi Mine is a primary underground mining with modern BIOX plants and engineered tailings and engineered TSF, not a tailings reprocessing operation. This shows that Ghana's technical capacity also has a big gap, but there is no ego retreatment project yet exists here. Now to the discussion, where all the 5 lenses meet. First one is reinforcement. Taquet-free milling or matches the conventional CIL routes proving at scale at DRG Gold Ego, the clearest near-term technical and economic fits. Furthermore, environmental remediation and public health improvements are intertwined, effectively the same outcome viewed through different lenses. We also have tensions. Bogoso's high grade is offset by refractory arsenic-bearing or needing cross-layer biooxidation. Grade alone doesn't predict which deposit to prioritize. Furthermore, Ghana's deposits rival South Africa's economy, but lack of ownership, clarity, and licensing pathway that makes South Africa succeed. These are some recommendations that Ghana should do next. 1, we have to develop a national policy dedicated to tailings reprocessing. 2, we have to streamline permitting across minerals commission. They are technically viable, that is, they are proven transferable recovery technologies. And also they are economically credible, that is, they are capital efficient at realistic scale and grade. They are environmentally urgent, that is, active remediation over passive containment, and also they are socially necessary, that is, health, jobs, and community trust all depends on it. This brings us to the end of the presentation. Thank you.
Okay, thank you very much, UMAT Takwa chapter. I think they address very important things in the presentation they just had. So we'll call on the next chapter, and that's UMAT SRID, to also present on what they have been able to do so far. Let's clap for them as they. So it's quite unfortunate the projector is not currently working, but kindly follow along with every single thing they are mentioning. All right, thank you very much.
Hello, good evening, and we are Team UMAT SRID, and we will be presenting on the topic Python-based software for acquiring and processing thin section microphotographs using a smartphone. So we'll go through the introduction, the problem statement, objectives, outcomes, the methods used, facilities used, and then the references are in the PPT. So if you're able to get a hands on them, you will be able to see it. So on to the introduction. Optical mineralogy is very important in geological exploration. And with that one, we are observing a thin section of a rock sample. And then we are going to pass polarized light through it to be able to observe the optical properties of that particular mineral so that we can then identify that particular mineral that is available. Now, with optical mineralogy, there are certain diagnostic features that are produced. So with the optical mineralogy, there are certain diagnostic features that are produced, and this is done by using plain polarized light or crossed polarized light. The plain polarized light is PPL, and then the crossed polarized light is XPL. So with the PPL, we have diagnostic features such as color, relief, cleavage, and then pleochroism. An example we can use is the cleavage. Whenever you observe a thin section of a rock sample, you'll be able to identify the cleavages that are present. An example can be an amphibole, which has 60 degrees cleavage and 120 degrees cleavage. Or maybe you can observe a pyroxene, which has 90 degrees cleavage. And if you identify pyroxene, you know maybe you find spodumene. And spodumene is the main lithium-bearing mineral, lithium-bearing ore for lithium. Diagnostic features for cross-polarized light. We have birefringence, we have extension, we have twinning, and then X solution. Another important one is the the extension rather. Now, with the extension, when a particular mineral is, when you get a rock sample and you place it on the optical what's it called? On the optical microscope, you'll be able to observe that particular minerals don't have the light passing through and they become dark. That is how you identify that is an ore. Then, in doing this, when you are taking the sample, you take thin sections. I've been saying thin sections, but you probably don't even know what it is. A thin section is a 30 micrometer thick mineral sample, and you usually get it from rocks. And that 30 micrometer thick sample, it is, when compared to a hair follicle, it is way smaller. So your hair follicle is, so the idea was that why not find a way that will be able to, perform analysis on a thin section of a rock sample and be able to identify the minerals in their correct percentiles, even on the field, without having to take them, now go to the lab, have them processed, and then you now observe them under the optical microscope. Due to the new advancement in technology, we know that this is simply saying that you are creating a framework that does so many things together. Instead of you having to do one thing, send it into another software, take that one to another software, but you have just one software doing all the other things together. And that is what we are working on. That is what has actually been done, not just been working on. So this opened up the opportunity to be able to use the programming language, which is Python. If you know Python, then you know its capabilities in machine learning. So the idea was that you'll be able to develop a software so that we can use that one to then attach it to a petrographic microscope, a mini one on the phone. It will be able to take a picture of the rock sample, then it will analyze the minerals that are inside the rock sample in its right percentiles. And with this project, it aligns more with the Sustainable Development Goals number 9, which is industry, innovation, and infrastructure. And the objectives of the project were as follows: to ensure that we produce a consistent image quality by reducing aberration, to save time and effort so that we can reduce human errors, to create an organized system for mapping and accessing images so that we can reduce data loss and improve the workflow of geologists, and then to identify minerals while providing their occurrence in a thick section as percentages. So with the outcomes, we were able to produce the quality images, time and effort was reduced, the data loss was also minimized, and then the minerals we were able to identify the minerals in their percentages with the thin section. So we used various methods, started with a literature review, then we did a software design. So it was a web app. So you go online, you are able to connect to the website, then you use it as a web application. So you can take the picture, you send it into the web app, then to perform all the necessary things that it has to do. So the high quality smartphone image feature, which then processes it with an image processing algorithm. It will launch into continuous improvement. It will test user feedback, develop image storage and retrieval system. Then it will now calibrate the data input into what you are looking for. So the facilities that we mainly used were Python, Google Colab, and then GitHub. And that was what we were able to do. This is the end of the presentation. Thank you.
Great, thank you very much. So we'll call shortly on the WAIMM UNE chapter to present as well. And then we proceed after that. So kindly give them a round of applause as they move up here on stage to present. Let's continue to clap for them. Let's continue to clap for them.
Yeah, hello. We are Team UNE, and my name is John Randolph Oche. So our project is design and implementation of an IoT-based digital twin for an electric motor performance monitoring. So we've realized that in the industries, the use of motor is about 30% to 50% in the industry. That is, they use motors in crashes, conveyor belts, and then hoist in the industry. So we've realized that motor is mostly used in the industry, but they are always exposed to faults. That is thermal stress. We have electrical stress, and then what? Mechanical stresses. This is what our project, we are going to solve the electrical aspect of it by a bit of the mechanical aspect, that is the vibration aspect. And then when we realize that the problems in the industry, one, the traditional monetary limitations, we've realized that in the industry, they mostly, or some industries mostly rely on reactive maintenance. Someone asks, what is a reactive maintenance? Reactive maintenance is when you have a fault and then you get the fault before you go and work on it. So that is reactive maintenance. So it means that when you keep on doing that in the industry, you are going to run at loss. So you need to have a system that can tell you a fault that will happen, let's say in 2 hours time or 3 hours time, before you can go and access the thing without damaging the real system. So now in this industry, some have the reactive maintenance scheme, which is not good, and they run at loss. So in the periodic maintenance, there's periodic maintenance. The periodic maintenance too is what they mostly term as the preventive maintenance. So they have specific days where they go, let's say on Tuesdays, we have preventive maintenance. So Tuesdays, that is when they go and work on some motors and some of the equipments in the company. But let's say before Tuesday and something happens to the motor, you are going to run at loss. So this our project is going to what? Solve that. It will tell you the problem before you get there. Now, lack of real-time data of what is in the industry. So these motors, they are there, they are working, they don't have access to their temperatures, their currents they are consuming, the voltage they are consuming. So with our system, we are going to solve that. We are going to have a system, a twin, which you can have access to your raw motor. In the industry, the physical aspect is there, and then you have the twin on your laptop. So whatever is happening there is also happening on your laptop. Any data that is, anything that the motor is consuming, the data is also seen on your laptop. And then inefficient fault detection. So there's difficult to detect early faults in the industry. Overheating and overcurrent are sometimes unnoticed. And then also limitations of existing systems. So some of the systems, they feel that now we don't want to move forward. We feel like the one we have is okay. So that is what some of the industries are relying on, which is not good. It's causing a lot of cost in the industry. So we have to move forward. And I don't know if you know, we are currently moving to the industry 4.0, where it involves the IIoT, that is Industry Internet of Things. So we need to also move forward so that in our industries, things will be easier there. Now, what is the objectives of our project? Our project, we are going to develop a digital twin. That is, we are using a software named AWS Twin Maker. So we are going to create the physical motor on our laptop, and whatever that is happening there, we can see it on it. And then we'll be acquiring the real-time data. Also, that is, we are going to implement the IoT communication. So what will be giving the information from the motor to your laptop is what is called the IoT communication. So we'll be implementing all those things. And then real-time synchronization. So some of the motors in the industries too, you see, they don't have real-time. So the thing has to happen. You go there and check and come and keep the record on your laptop. some of the motors or some of the industries, that's what they do there. But with this one, it is real-time synchronization. Whatever is happening there is giving you live feed on your laptop. And then that is, we are going to build a visualization dashboard. So that is where we see our motor on our laptop, and whatever that is happening on the physical aspect, we can see it there. And then we are going to detect fault early. So in terms of digital twin, so digital twin is something that it involves IoT and then what predictive maintenances. So if you have this set of data always, it means that you can detect, you use this data, feed it to Python or machine learning, big data. You can feed it there, and then it can tell you when a fault can happen. And it won't let you, maybe you won't be doing reactive maintenance or periodic maintenance. This one, you'll be doing predictive maintenance. So it means that you can predict in the next 2 hours, this is what this is what is going to happen to my motor, and you go and work on it. So now, we have different kinds of digital things. So we have the digital models, digital shadows, and what? Digital twin itself. So with the digital model, it is when you have your physical components there, your laptop too there, you go there, take whatever is happening on your motor, give it to the laptop. If you want to control it, you go there and control the motor. That is a digital, that one we call it digital model. You go there, do the thing by yourself, take the data on the motor, give it to your laptop. If you want to control the motor, you go to the motor itself and then either off the switch or do anything. That one you are doing it physically. And we have digital shadow. So with the digital shadow, your physical component can feed real-time data to your laptop, but you cannot control your motor with your laptop. So that is also a digital shadow. And now the digital twin, which is in the Industry 4.0, that is where you can receive real-time data from the motor to your laptop, and at the same time, controlling your motor from your laptop. So that is what we term as what? A digital twin. And now, what are we going to do for our project? First, let me address some of the existing systems that are inside the industries. So in the industries, they have SCADA systems, that's supervisory control and data acquisition. Yes. So with that one, it gives real-time data. So that one answers what is happening to the motor. How can I control it? But with this digital twin, it is what is happening to the motor, or what will happen to the motor, and what if I do this to the motor? You see that? So the digital twin answers why something is happening, and then what will happen in the future too. So we are going to what? First, our methodology. So we've planned on what? Getting the physical layer, that is the motor itself, and then getting the components, that is current sensor. We are going to take the current reading of our motor, voltage reading of our motor, and then speed, and then the vibration also from our motor, and I said temperature, and then also the humidity, the environmental temperature, that is humidity and the what? Yes, the environmental temperature. Now, our second method is going to be the data acquisition. So that is where our IoT components comes in. So the key microcontroller that we'll be using is the ESP32. The electrical, this is more of electrical. So the ESP32 is what will be giving us, will be taking the data from the motor to our laptop. And then we'll build the digital twin on our laptop, and then the synchronization takes place. That is connecting the physical asset to the digital twin, and then the synchronization takes place. And then we'll see the performances. And then, if possible, we run the motor for a certain time, feed the data to a machine learning, but then we'll do a predictive maintenance. That is using some of the prompts and then the code from Python to check the predictive maintenance of the motor, because we can't just, whilst the motor is running, you can't get the data, you can't know what will happen in the future. You have to get an amount of data before you can do that predictive maintenance. Now, with this one, I wish you have seen it, but it's not. This is the architecture of our motto. So first is the physical asset. That's the twin maker where we can make the visualization there. And then Amazon S3, that is where the data that is being running is being stored. And then if possible, we can take it to go and use it for the predictive maintenance, and then our dashboard. So now currently we are done with the PCB design and we are going to print it outside. And then we hope when it comes, maybe we can also share it to you people, and then you see. So with this one, we are mostly solving most of the mining faults. That is the reactive maintenance, the periodic maintenance. So ours is more based on the predictive maintenance. So we don't want the cost to happen before you can go and work on it, because it is it's difficult that every week you are going to buy a motor. So that one is no good. So you have to have a system that can tell when the motor you can tell when the motor is faulty, or you can know what is happening to your motor. So that is our system that we are building as Team UNE.
Thank you, Team UNE. So we've come to the end of this amazing student conference, and it's been an awesome time, from the keynote sessions to the panel discussions, and then to our student report and presentations. So we would want to invite our executive chairman, Mr. Lawrence Omari, to give us the closing remarks of this conference. Let's clap for him as he joins me here on the stage. Let's continue clapping.
Yeah, thank you very much, everyone. I believe we've all had a nice time. You probably will have to forgive me. When it gets to this stage, I can't speak English anymore. But I don't know if you can. Can you speak English at this time? Thank you. So bottom line is we're done for the day. I think Era did a good summary of what happened today. I wouldn't want to go back again. But what I can assure you is that going forward, we need to do more. We need to see big things. I'm very impressed with the level of innovative projects. Let's keep going. The only challenge was that we couldn't get these things done. Just because everybody was presenting here, and in actual fact, we used the machine here to set the points. It's a shame we made those presentations, but then we'll get all those to you. Tomorrow is another day. Tomorrow we need to set off very early. We were originally supposed to go to about 7 mines, but as it stands now, we'll be going to 5. We will not be going to Insuta and then Nzima. That's Adamus and then GMC. We had a bit of a numbers issue. But we're going to the rest. Wasa, as in Golden Star. I am free, Perseus Mining. Next door, Anglo Ashanti. AB, Go for Stakwa, and then Daman. So yes, be prepared, get up early. They should probably might have sent the list by now. If not, I mean, just even try, get to see where you're going. They had to blend it, so it's difficult to say this school will go here, this school will go here. No, we had to blend as such. And we are not just going, like I said this morning, you don't just go, sit, stand like a tree or a stump. No, the shaking should come in. Go and shake yourself, get to understand things, learn something, ask questions. Make sure you go there empty and come back full. Because, like I keep saying, You didn't come all this way just to come sit down. You came to get something meaningful. Make sure you leave with something meaningful. Folks, I want to thank everybody who came from my side. I think Era will conduct the vote of thanks later on, but I want to thank everybody who came. You might have gone or have some one or two issues, but that's how it is in the industry. There's no rosy or roller coaster way of just getting things done. The problems come in, but you always have to maneuver and solve the challenges. You go to work tomorrow morning expecting to have a normal day, you go and meet problems. You don't just turn your back, you fix it. Let's have that sort of Let's go and rest. If you are like me, you can just, there's some joint somewhere here along the line. You can go chill up tomorrow, wake up at 5 a.m. and go to work. Thank you very much. Enjoy yourself this evening.
Thank you, Mr. Lawrence. So